Hi, welcome to Expertisor Academy. This is Kiri, lecturer in physics. In this video, we discuss about the Maxwell's correction to Ampere's circuital law. Maxwell's correction to Ampere's circuital law. Here, here we discuss the Faraday's law of induction and its different ways. We studied Faraday's law of electromagnetic induction, which states that change in magnetic field produces an electric field mathematically. So look at this. This is the electric flux, closed integral, that is equal to closed integral E into d. Electric flux, that is equal to minus change in magnetic flux. So that is equal to change in magnetic flux resembles the electric flux. So that means change in magnetic field produces electric field. That's all. So this part is the electric field induced along the closed loop. So first one is the electric field induced along a closed loop. So this one is equal to variation of magnetic flux with time. So change in magnetic flux with time. So that is equal to induced electric field. So these both are is equal to changing magnetic flux phi v in a region enclosed by the loop. So change in magnetic flux enclosed in one loop. So here magnetic flux, that is equal to change in electric flux. So this one gives the magnetic flux. Here electric flux is equal to electric flux, change in electric flux. This one gives magnetic field. So this part represents magnetic field induced along the closed loop, that is equal to variation of electric flux with time. Variation of electric flux with time. So that one is equal to changing electric flux phi E in the region enclosed by the loop. Changing electric flux phi E in the region enclosed by the loop. Here, in order to understand how the changing electric field produces magnetic field. Changing electric field produces magnetic field. So let us consider the situation of charging a parallel plate capacitor shown in figure, assuming that the medium between the capacitor plates is a non-conducting medium. Here, this is the parallel plate capacitor. First one is positive, second one is negative. Here we are representing one battery. So here I suffix C is the current of the capacitor. So here magnetic flux is equal to mu naught into capacitor current. So one plate is generates the one enclosed surface. Here the distance between the electric field and a positive charge, that is small d. So in this space there is no propagation of any charge, so that's why the magnetic flux is zero. Here the charge propagation is generates, so that's why double closed integral electric flux, that is equal to 1 by epsilon naught times of net charge in this transaction. So this one represents the Gauss law. Next, change in electric flux, that is equal to 1 by epsilon naught into change in charge. Change in charge here representing the current ID, that is equal to epsilon naught into change in electric flux. So here this ID represents the displacement current. Displacement current can be defined as the current which comes into play in the region in which the electric field and electric flux are changing with time. So here this magnetic flux, that is equal to mu naught I, that is equal to mu naught into IC plus ID, where I is equal to IC plus ID, which means the total current enclosed by the surface is sum of conduction current and displacement current, which means the total current enclosed by the surface is sum of conduction current and displacement current. When a constant current is applied, displacement current ID equal to 0, and hence IC is equal to I. Between the plates, the conduction current IC equal to 0, and hence ID equal to I. So here between the plates, conduction current IC equal to 0, and hence ID equal to 1. So in this video we discussed the displacement current and Maxwell's corrections. Here the induced electric field gives the magnetic field. That means change in magnetic field gives the electric field. Here the change in magnetic field is equal to a change in electric flux, that is equal to change in magnetic flux. So here we are considering the parallel plate capacitor, and also here observe the displacement current and the conduction current by the propagation of charge from positive terminal of the conductor capacitor to negative terminal of the capacitor. So this is the information about displacement current and Maxwell's correction to Ampere's circuital law. Thanks for watching this video. For more videos, visit www.expertisoracademy.com. Thank you.